Hello again, students. So, the goal of this particular recording is to prove the theorem, which in the notes is called Theorem 3.2.2, which says that, and I know I'm pointing at something that doesn't say exactly what I want, f is continuous at, so if u is a subset of R, and f is a function defined on u, and p is in u, then f is continuous at p, if and only if, this is just a symbol for if-then, if f is continuous at f is continuous at p if and only if for every sequence xn of elements of u, if xn converges to p, then f of xn converges to f of p. But I want to prove an if and only if, so I need to prove two implications. I need to prove if this, then that, and I need to prove if that, then this. So let's go the forward direction first. Let's suppose that f from u to R is continuous at p, and that xn is a sequence of elements of u such that xn converges to p. So why is that the right thing to assume? Well, I want to assume f is continuous at p. And now I need to prove something is true for every sequence of elements of u. So let's consider any sequence of elements of u. I need to prove that if xn converges to p, then something happens. So I get to assume the hypothesis is true. Let's assume xn converges to p. I need to prove f of xn converges to f of p. So this is like an epsilon n proof. And, well, let's see what we can do. So let's sketch the proof off to the side. So my eventual goal is, I need to show for every epsilon bigger than 0, there exists a choice of big N such that for all little n bigger than big N, absolute value of f of x sub n minus f of p is less than epsilon. That's my goal. That's what I need to show. So I should start by saying something like let epsilon be bigger than 0. And my eventual goal, I need to come up with a choice of big N, of course, but my eventual goal is absolute value of f of x sub n minus f of p is less than epsilon. Well, one thing I know is this function f is continuous. So for some choice of delta, if I can get absolute value of x sub n minus p to be less than delta, then that follows. As long as delta is chosen appropriately, that is, delta should be chosen because f is continuous. But I know that xn converges to p. So this follows whenever little n is bigger than big N for some big N. Oh, neat. So this is actually the proof. I need to come up with a choice of delta using the continuity of f. And then I need to use the fact that xn converges to p to come up with a choice of big N. Then I'll suppose that little n is bigger than big N, and I'll follow these arrows. There's the proof. Let's just put it into words now. So let's suppose that f from u to R is continuous at p, that x sub n is a sequence of elements of u such that xn converges to p. I want to show that f of xn converges to f of p, so I should start by considering any epsilon bigger than 0. And the first thing that I did over here, chronologically, not by space or anything, is I wrote this down. So let's write that down right now. There exists a choice of delta bigger than 0, such that for all x in u, if the absolute value of x minus p is less than delta, then absolute f of x minus f of p is less than epsilon. But wait, I know that delta is bigger than 0 and that x sub n converges to p. By the definition of the limit of a sequence, I know that there exists some big N such that for all little n bigger than big N, absolute value of x sub n minus p is less than any positive number that I want to consider. there's the positive number that I want to consider, because if I can get x sub n minus p to be less than delta, then I can use this implication. So let's use that choice of delta. All right, so now, I mean, it's basically done. Consider any little n bigger than this big N. So consider any little n bigger than big N. Then I can use 3.5. 3.5 says that whenever little n is bigger than big N, then absolute value of x sub n minus p is less than delta. So 3.5 says absolute value of x sub n minus p is less than delta. Maybe I'll add a little sentence right here. By assumption, x sub n is in fact an element of U. So now what do I know? I know that xn is an element of U, and I know the absolute value of xn minus p is less than delta. So I can use item 3.4, which this is item 3.4, to conclude that absolute value of f of x minus f of p is less than epsilon. Nice. So what have I proven? Well, I started, hopefully at some point, I started by considering any epsilon bigger than 0. I came up with a choice of delta. That was important in the proof, but not in the statement of the theorem. I came up with a choice of big N. I considered any little n bigger than that big N, and I concluded that f of x sub n minus f of p, that was poorly drawn, I proved that f of x sub n minus f of p is less than epsilon. So I've proven that for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, there should be a comma there. Absolute value of f of x sub n minus L is less than epsilon. This means that f of x sub n converges to f of p. Since x sub n was any sequence of elements of U which converges to p, I get the desired result. So there's the forward direction. Now let's do the reverse direction. It won't be that much harder. So I need to prove that if for every sequence xn of elements of U, if xn converges to p, then f of xn converges to f of p. If that is true, then f is continuous at p. I will choose to, instead of proving that, I will prove the contraposition of that. I will prove that if f is not continuous at p, then the negation of this statement follows. So let's figure out what we actually need to prove. By negate, I'll suppose that f is not continuous at p. I need to prove that not this happens. So let's see. The negation of a universal is an existential. I need to prove there exists a sequence x sub n of elements of U such that xn converges to p and f of xn does not converge. You know what? I have colors, so it's does not converge to f of p. And in order to pull that off, let's negate the definition of continuity and see what we get. So I'm going to put the actual negation in the space right here, but off to the side, I'll figure out what that negation should be. So I want to assume, what do I get to assume? I get to assume not f is continuous at p. So I get to assume not for all epsilon bigger than 0, there exists a choice of delta bigger than 0 such that for all x in U, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. So negating all this, gives me, well, negate a universal, so it's not true that for every epsilon some stuff happens. So there must exist an epsilon so that all of that stuff does not happen. There exists an epsilon bigger than 0, such that negate this existential modifier will give me a universal modifier for every delta bigger than 0. Negate this universal quantifier will give me an existential quantifier. There exists an x in U such that negate an if-then, that must mean the hypothesis is true and the conclusion is false. That's the negation of an if-then. There exists an x in U such that the hypothesis is true, x minus p is less than delta, and the conclusion is false. Absolute value of f of x minus f of p greater or equal to epsilon. All right, so let's write that down. Because f is not continuous at p, it follows that there exists an epsilon greater than 0, such that for all delta greater than 0, there exists an x in the domain U, such that absolute value of x minus p is less than delta, and absolute value of f of x minus f of p greater than or equal to epsilon. And I know that that's true, right? Because I want to prove if f is not continuous, then something happens. So this is something that I get to assume is true. So I know that that's true. All right. That's also called item 3.6. So let's consider that choice of epsilon. So for that fixed choice of epsilon, I don't know how big it is. It's bigger than 0. It could be 1/10, it could be 1/1,000,000th, it could be 5. But it's just some number, positive number. Let's let delta n be equal to 1 over n. I know something is true for every positive number delta. Is this number positive? Yeah, sure is. So that must mean there exists some x in U which depends on delta. My choice of delta depends on n, so I'll call it x sub n because it depends on the choice of n, such that absolute value of xn minus p is less than delta n, which recall is 1 over n, and absolute value of f of xn minus f of p is greater than or equal to epsilon. Great, so let's actually just see what we have and how this compares to what we want. So this gives me a sequence of elements. That's nice. I see xn minus p is less than delta n, which is 1 over n. Ah, we've seen how to deal with that. That should mean that xn converges to p. That's what we want. I know that f of xn minus f of p is always bigger than or equal to this fixed epsilon. Well, if f of x sub n converged to f of p, then eventually I would be able to get this quantity to be less than epsilon, but I can't. So that means f of x sub n does not converge to f of p. This will do the job. Let's just put that into writing. All right, so let's write everything down. So I know that xn is in U for every natural number of n, so xn is a sequence of elements of U. Now I have absolute value of xn minus p is less than 1 over n for every natural number of n. And I know that 1 over n converges to 0. From that, we can see that xn minus p converges to, converges to p. So xn itself must converge to p. That's a different argument using, if you like, limit laws to get the result instead of composing a direct epsilon n proof. Additionally, I have that for every natural number n, f of n minus not p, but f of p is greater than or equal to epsilon. So in particular, let's actually phrase it this way. If f of xn converges, so if it converges, then, well, limits interact well with inequalities, especially loose inequalities, and they interact well with absolute value pairs, then I'll get the absolute value of the limit of f of x sub n minus f of p is greater than or equal to epsilon. So f of x sub n does not converge to f of p. And let's maybe explore the logic here. So if it converged, then it doesn't converge to f of p. So either it doesn't converge or it does converge to something other than f of p. So thus we have produced a sequence xn of elements of u such that xn converges to p and f of xn does not converge to f of p. Thus, what have we shown? We've shown that if f is not continuous at p, then there exists a sequence xn of elements of u such that xn converges to p and f of xn does not converge to f of p. Now, as we've already seen, both of those are negations of statements. So what we've really shown is that if not f is continuous at p, then it is not true that for every sequence xn of elements of u, if xn converges to p, then f of xn converges to f of p. Now, by the principle of contraposition, this means that this thing in parentheses implies that thing in parentheses. So, writing that, the principle of contraposition now concludes that if for every sequence x sub n of elements of u, if it follows that xn converges to p implies that f of x sub n converges to f of p, then f is continuous at p. So what does that mean? That means if you want to check that a function is continuous at a point p, instead of trying to come up with an epsilon n proof, you can instead go for a sequence-based proof. You consider any sequence of elements of u, you can assume that xn converges to p, and you can try to prove that f of x sub n converges to f of p. Because if you know that this is true, then you know that the function is continuous. Nice. That completes the proof. I'll stop right here. I'll upload another video which will seem really similar to this video, in which I'll talk through the proof of the remaining result in this packet, which says that something similar happens, but instead for sequences, instead for limits of functions instead of for continuity. Great. I'll talk to you in the future. I hope that everyone's staying reasonably sane with social distancing. Talk to you soon.